for coming to our presentation. And we're Team Chiba, and it's so great to be here. So first, I'd like to introduce our team shortly. And we're all 17 members, and 15 of us are coming today, all the way from Japan. And all of us major in chemistry, so we didn't know anything about biology when we started iGEM. But yeah, we had engineering mind, and yeah, it's really exciting to begin a new thing, we thought. And also, we've got many help from the supporters, and it's in the right in the screen. And some companies gave us money, and others give us Phoebe oligos and cool instruments and stuff. And thanks to them, we somehow managed to come here to presentate. So, yeah, and here's the map, and we came from the Far East out of Tokyo, and that's the Japan's big screen. And I think we're so close to Tokyo Alliance, but a little bit in the east of that. Sorry. Yeah. So, and these are the projects, and we have many projects in the first time, and like these are the picture of Professor Umeno's, and it's so cute. And finally, we have 4 projects, and 3 of them, Swimmy bacteria and aromatic E. coli and balloon E. coli, is using a light sensor that the UCSF and UTexas made it last year. And we're gonna change the output. And the last one is E. coli, and they're trying to make a bacterial clock by the Chi system of the cyanobacteria. And yeah, goes the first project, and from Swimmy bacteria.
Hi, I'm Tomoki. We are Swimmy bacterial team. Our goal is very simple. First, we want to stop the movement of E. coli by illuminating light. Oh. Next, we use a mask. Here, E. coli frees its movement. Where the light is on, E. coli outside the zone are moving around, and it's finally captured there. Thus, we draw a picture. Then we move the mask. This is a point. Unlike the famous colloid reported in the last year, our system's picture is transient, and the picture can move again and again by changing mask, like a movie, like animation. Wild type E. coli is switching between running and tumbling. According to the paper by Professor Parkinson, some mutant of TSR is a chemotaxis receptor for serine, makes E. coli tumble. Another kind of TSR mutant makes E. coli run. Using this, we designed this system. Here, whole system is regulated by OMPC promoter. We can simply plug this system to the right sensor developed in the last year. So So we confirm the effect of the expression of TSR mutant. Microscope assay. We put the TSR tumble under the arabinose promoter. We measured the migration distance of E. coli, both in arabinose and arabinose-free condition. The red one is arabinose condition, where the TSR tumble is expressed. The gray one is off condition. As you see, TSR tumble significantly slowed down E. coli's migration. We also conducted capillary assay. Here, we mixed the two cells. The left one is expressing TSR tumble, and the other is expressing MRFP instead. Oh, sorry. To the mixture, capillary fixed with LB dipped. Here, the migrating E. coli can get into the capillary more than the one tumbling. We counted the number of each E. coli by plating. As you see, E. coli having TSR tumble slows down upon adding the inducer. We also tried swarm plate assay, but we see very subtle effect of TSR tumble expression on this format. We ran TSR tumble rarely changes the swimming behavior of E. coli. And things yet to be done assemble food construct and connect with the right sensor and draw a picture, then make a movie. Thank you.
Hi, I'm in the aromatic E. coli team, and we aim to create E. coli that produce aroma. We'd like E. coli to emit various aroma that responds to light. And first, I would like to explain the synthetic pathway of terpene. Starting from isoprenoid pathways, GPP and FPP are produced. They act as a precursor of aroma terpenes. Naturally, these precursors lead to production of biomass. By introducing aroma synthases, you can generate a variety of and completely different smells. Sorry. Aroma terpenes has additional values such as relaxation effect. Okay, I'll go on. This is the final construct in our hand, and with osmotic pressure, geraniol is produced while pinene synthesis is blocked by CI inverter. When the osmotic shock decreases, production of geraniol is replaced with pinene. This circuit has just been constructed on November 2nd, 2 days ago, so phenotype hasn't been tested yet. But by the way, geraniol and pinene compete for the same precursor, and that means sharp switching is possible.
Before testing the whole system, we evaluated scent generating devices by human nose. That's my nose. The chart shows the result of it, and we have 5 types of genes that produce aromaterpenes. And we could feel the unique smell for 4 syntheses. The scent was significantly enhanced with co-transformation of IDI, which increases the precursor supply. Among these 4 aromas, we liked geraniol and pinene the best. This is about a little far future. By creating a circuit with different amount of output for each aromas, you can create your own favorite smell. It's a novel method for making a best blend of aromas. I will be the first expert of bacteria producing aromas. This is aroma evolution.
Hello, we are team of Balloon E. coli. Our project is to make E. coli big in the light. We think it's interesting that E. coli swell like a balloon in the light, and E. coli shrink in the dark. We wonder to what extent can it go. Can we see E. coli with naked eyes? In addition to our pure curiosity, and there are several motivations to go for this project. Maybe E. coli can be fact-sorted easier. Maybe E. coli produce more protein as cell.
This is strategy we have chosen. FTSC is a gene required the septation. Dysfunction of this gene lead to the long shape like a noodle. Lot A is a gene that keeps a cell rod shape. If lot A malfunction, E. coli becomes spherical. This is what we design. We harness light sensor to the following system. Here, when the light is off, on-power promoter turn on the FTSC. Thus, E. coli retain its septation. Also expressed is the CI repressor that turn off the lot F mutant expression. Thus, E. coli keep its normal shape. Now, when the light is turned on-power promoter turn off the FTSC, and instead, CI promoter turn on the lot F mutant expression. By this fashion, FTSC E. coli form long shape, but it will not just a noodle. Lot F mutant are also expressed. E. coli will grow big like a balloon.
To obtain lot A mutants that makes E. coli spherical, we created lot A libraries and expressed in E. coli. We got the lot A mutant using a microscopy. By the way, Minshi deletion strain originally forms noodle-like shape. When we expressed the lot A mutant we isolated in this strain, E. coli indeed became spherical. However, the size of it is more shorter than the original one. Next, we evaluated the inverter unit. To test this function, we transformed this unit into on-power dilution strain and no-dilution strain. In on-power dilution strain, on-power promoter turns off the CI repressor expression and CI promoter turns on the RFP expression. In no-dilution strain, on-power promoter turns on the CI repressor expression, and CI promoter turn off the RFP expression. OMP-R dependency was observed. First, mean sheet strain formed noodle-like shape. Second, we got the ROT A mutant that makes E. coli spherical. Third, ROT A expression in delta mean C strain result in small and spherical shape. Fourth, inverter constructed OMP-R dependency was confirmed. Thank you.
Hello, we are Ecoloc team. Ecoloc is self-cycling E. coli. Installing Kai system, E. coli starts oscillating. Kai system, 3 proteins are generating 24-hour cycle. This is the most simplest circadian system. But it is not known how this oscillation regulates global expression of many proteins in cyanobacteria. SAS-A is sensory kinase. SAS-A is believed to connect with Kai cycle and transcriptional oscillation and many proteins. RPAA is a cognate response regulator for SAS-A, and its deletion results in the complete loss of transcription oscillation. This is all known about Kai. Believe that SAS-A is communication with Kai oscillator. Believing that RPAA communicates with SAS-A, we designed RPAA OMP-R Kaimura in hope that we read out Kai oscillation using OMP-C promoter.
In general, response regulator has two domains. Regulated domain receives phosphate from histone kinase. Effector domain binds to specific sequence of DNA, as is the procedure shown here. We create 36 chimera of RPAA and OMP-R. They are different in cutting point, but all of them have the receiver domain of RPA to communicate SAS-A, and DNA binding domain from OMP-R to bind and activate right to OMP-C promoter. We have just finished the construct of them, but we ran out of the time at this point. Time is up for IGEM 2006, but this is what we plan next. Chimeras along with wild-type RPAA and OMP-R will be tested in their function as response regulator. Just switch on off the OMP-C promoter. And we hope we found some chimeras that indeed pick up Kai cycle. Thank you.
And that was our fourth project. And we learned a lot about bios during this summer, and that's what we thought about. And about the abstraction, even working at the system level, we thought we still need a minimum knowledge or experience on the parts. And for example, we spent months just to find out the right condition to use the CI inverter. But now we got enough experiment in biology, so I think we can come back next year and try. And yeah, that's it, and thank you very much for listening. It was very great to come here. Thank you very much.
I have a question for your team. So given you're rookies and now you have some experience, if you were to bet on one of these projects to go forward with in a short time frame, which one would you take on?
So, you mean?
So if you found yourself at the beginning of summer right now, given the work that you've done, would you continue to work on all four? Would you take one of these projects forward?
From now.
From now, if you had to start from now. Now that you have some basic understanding.
So,
In my opinion, I think I'll choose one because doing four at the same time is pretty hard mentally and both physically because the experiment room is like very small, so it's hard to do four things at the same time. But we have a lot of members, so maybe like
maybe two.
maybe good.
Any other questions? Okay. Let's go.